tasks results from switching to efficient strategies. Abstract. It is debated whether training with a working memory (WM) task, particularly NBAC, can improve general WM and reasoning skills. Most training studies found substantial improvement in the trained task, with little to no transfer to untrained tasks. We hypothesized that training does not increase WM capacity, but instead provides opportunities to develop an efficient task-specific strategy. We derived a strategy for the task that optimizes WM resources and taught it to participants. In 2 sessions, 14 participants who were taught this strategy performed as well as 14 participants who trained for 40 sessions without strategy instructions. To understand the mechanisms underlying the no instruction group's improvement, participants answered questionnaires during their training period. Their replies indicate that successful learners discovered the same strategy and their improvement was associated with this discovery. We conclude that NBAC training allows the discovery of strategies that enable better performance with the same WM resources. Working memory, WM, is defined as the ability to simultaneously retain and manipulate information within short time periods. Baddeley, 1992, 2003. The number of items that can be explicitly accessed and manipulated, i.e., WM capacity, is extremely limited and poses a strict bottleneck to human cognition. Cohen, 2001. Indeed, WM capacity is strongly correlated with fluid intelligence. Engel, Laughlin, Tucholsky, and Conway, 1999, Suss, Oberauer, Whitman, Wilhelm, and Schulze, 2002, and with academic achievements. Baddeley, 1992, Bayliss, Gerald, Baddeley, and Gunn, 2005, Hitch, Tose, and Hutton, 2001, Swanson, 2004. One of the most studied WM tasks is the NBAC task, example, Jakoby, Bushkuhl, Jonides, and Parikh, 2008, in which participants are presented with a sequence of serially presented stimuli and are asked to respond when a stimulus is repeated at an interval of exactly n stimuli. This task requires holding the last n items, plus the new item, in WM. When each stimulus is presented, participants must compare it to their predicted target stimulus, the item presented n intervals earlier, respond if there is a match, target, and then update their WM representation to form a prediction for the next target stimulus. Since performance in this task is highly correlated with general intelligence scores, even compared with other WM tasks, Jakoby, Bushkuhl, Parikh, and Meyer, 2010, it has become a common task for training aimed at generally enhancing WM and fluid intelligence. Example AU et al., 2015, Reddick, 2019, Schweihofer, Fischer, and Booner, 2015. In this study, we chose to use a spatial NBAC task. In the past, we had trained a group of participants with this task, with no explicit strategy instructions, for 40 sessions. Jakoby et al., 2019. Most of those participants improved significantly in this task, but showed no transfer to other WM tasks. We now asked what these participants had actually learned during this training, and whether a similar degree of improvement could be gained in less time if participants were explicitly taught the efficient one-update strategy. Results. Improvement was substantially faster in the strategy instruction group. Initial performance without instructions. Performance during the first session, measured by mean n per session, did not differ between groups. Strategy instruction group, mean n equals 2.65, SD equals 0.37, 95% confidence interval, CI, 2.46, 2.84. No instruction group, mean n equals 2.43, SD equals 0.44, 95% CI, 2.2, 2.66, P equals 0.38, in a two-tailed, two-sample unequal variance t-test, Cohen's d equals 0.4. The second session began with an instructional video clip for the strategy instruction group, and with no specific instructions in the no instruction group. Afterwards, both groups performed the same task, with the same adaptive protocol, see method section. Mean performance in the second session significantly differed between the two groups, with the n of the strategy instruction group, mean n equals 3.25, SD equals 0.43, 95% CI, 3.02, 3.48, being significantly higher than that of the no instruction group, mean n equals 2.56, SD equals 0.58, 95% CI, 2.36, 2.82, P equals 0.002, Cohen's D equals 1.29, as shown in Phi. Discussion and conclusions. Our results indicate that training-induced improvement in the N-back task can be fully explained by the discovery of a task-specific strategy. Hence, improvement does not indicate a general enhancement of WM capacity. This finding explains previous findings of no transfer, or only very near transfer to other types of the N-back task, example, Jakoby et al., 2019, Linares et al., 2019. Based on our results, we predict that performance in untrained tasks will improve only when the discovered efficient strategy applies, and its relevance is transparent to the participants. Thus, performance in tasks with the same structure may be improved, Fellman et al., 2020, Reddick, 2019, as previously reported, Linares et al., 2019. However, performance in most other WM tasks, and even in N-back tasks for which the strategy is difficult to implement, Jakoby et al., 2019, is not expected to benefit from the discovery of this strategy. This account is in line with the proposal of Gathercole et al., 2019, who claim that training-induced transfer occurs only when participants have acquired a new complex cognitive skill during training, and when that skill can be applied to a novel task. Though to the best of our understanding, the same efficient strategy was repeated across participants, we do not claim that this is the only possible strategy. Yet, theoretically, we expect all efficient strategies across WM tasks to have something in common. In fact, and as mentioned before, our strategy is the same or very similar to the strategy described previously for N-back with letters, Lane et al., 2018, and with digits, Fellman et al., 2020, in their studies characterizing the continuous effect of training with and without an explicit strategy. We assert that all efficient strategies reduce the number of manipulations in WM per trial, compared with the naive strategy. Importantly, there is no need to reduce the total number of operations per trial, only the operations that put load on WM. For example, scanning through items without changing their slot in WM does not add to WM load, Myers et al., 2018. This training study provides further support for the strategy mediation theory of WM improvement, Dunning and Holmes, 2014, Peng and Fuchs, 2017, compared with the capacity theory, Engel and Kane, 2003. The strategy mediation theory assumes that WM has a relatively fixed capacity and therefore claims that WM performance is determined by the efficiency with which its capacity is used. Bailey, Dunlosky, and Kane, 2008, McNamara and Scott, 2001. The capacity theory assumes that capacity can increase with practice and is often described using the muscle-like metaphor. Efficient training strengthens WM by increasing capacity, described by Peng and Fuchs, 2017. Yet most of the literature of strategy mediation theory does not specify the strategies that would be efficient for WM tasks. The description of rehearsal or chunking, McNamara and Scott, 2001, Peng and Fuchs, 2017, Turlianes and Whitfield, 2003, does not capture the unique structure of WM tasks, which are designed to require online manipulations that cannot be organized into fixed chunks, or at least not in any straightforward manner. Our study adds to recent studies, Fellman et al., 2020, Lane et al., 2018, in specifying an efficient strategy for the case of the spatial N-back task. Unlike N-back tasks that use items that can be easily named, like letters or digits, spatial tasks cannot benefit from subvocal rehearsal of the items. See Chewy and Logi, 2020. Still, subvocal verbalization can help memoizing which of the N items in WM should be updated in each step. The positive impact of strategy instructions had been recently studied. For example, Fellman et al., 2020, taught participants a specific strategy for the N-back task with digits via the internet and found that using this strategy facilitated initial learning. However, the advantage of explicit instruction, observed during the first few sessions, was partial, as the strategy group continued to improve throughout the 12 training sessions, and performance of the tutored and non-tutored groups was similar following the first few training sessions. Thus, instruction was beneficial, but its impact was smaller than in our case, perhaps due to the nature of internet training, or due to